Today, I'm going to talk for half an hour. I'm going to basically wrap up the things that Sturl was doing. Sturl is running a meeting of the committee that he chairs that is planning the future of NASA research in the area of the structure and evolution of the universe for the next 25 years. And they're meeting here at Caltech, and he's making sure that Lisa is in that roadmap plan. So he's away for a good reason. And so I'm going to finish up the last little bit of the things he was doing and then introduce issues of computing waveforms from in-spiral of compact binaries for LIGO. And then I'm going to turn it over to Alessandro Buonanno to talk about details of the waveforms from in-spiraling binaries. So let me begin by showing you this table of these are the best current numbers that are obtained by the techniques that Sturl was talking about in his lecture on Monday and last Wednesday. The best current numbers for event rates for LIGO and correspondingly for distances to which LIGO can see. I want to remind you of where these numbers come from. That is, that connects back to Sturl's lecture and how they compare to some extent with what Sturl quoted and what you've computed in a problem set for today. So what I'm listing are neutron star binaries, neutron star black hole binaries, black hole binaries, and then this last column I will comment on at the end. It's something that is obtained by techniques that Sturl has not talked about with sources that Sturl has not talked about explicitly. And so Sturl has described how for neutron star binaries one estimates the event rate in our galaxy from two observed systems in the field, that is, ignoring black hole neutron star binaries that may be in globular clusters, which have a very different kind of evolutionary history than in the field. The phrase "in the field" means things that are not in dense clusters and that therefore have a negligible amount of influence from their surroundings on how they evolve. And we have two known neutron star binaries that will merge in less than the age of the universe, and you go to the details of the searches that led to the discovery of them as binary pulsars, and you go through the kinds of complicated calculations and considerations that Sturl gave, and you wind up with an estimate that Sturl got of 10 to the minus 6 per year. You then ask yourself, what are all the ways in which things could go wrong? The principal ways in which things could go wrong will basically boost the event rate through types of systems that would not have been seen because they're born with, as Sturl gave a good example, they may be born with a separation that is sufficiently small that their lifetime is, say, only 10 to the 4 years until they merge. But if the birth rate is of the order of 10 to the minus 5 per year, that is one every 100,000 years, you wouldn't expect to see any. And so there are various ways in which things can go wrong. Another way in which things can go wrong is the statistics of small numbers. And when you look carefully at the statistics of small numbers, you find that almost always you seriously underestimate, if you use standard statistical techniques, you almost always underestimate the true number. I'm going to give you a paper which you can read, which goes through that very interesting issue that's by Calagera, Joe Taylor, Ramesh Narayan, and colleagues. So the bottom line is, after you go through looking at all the ways things could go wrong, the current number that people quote, and this is primarily from Calagera, Narayan, and Taylor, is 10 to the minus 6 to 5 times 10 to the minus 4 per year. And so the 10 to the minus 6 was the number that Sturl did at the blackboard for you, showed you how to get it fairly quickly, but the whole story is much more complicated. The distance to which you could see these systems with LIGO 1, if you do the analysis carefully, using the theory of optimal signal processing, which we will develop next term, you wind up with a number of 20 megaparsecs. You had an exercise today on which you were asked to compute this number. The number that I've forgotten whether it was Mihai or Yanbai came up with was 24, I believe. Was that who was that in the official solution? Yanbai. So he got 24. But of course, you knew what the number was, and it was supposed to be an advance. So Anyway, you see how to get that number in the exercises that I gave you for today. You then extrapolate out through the universe using the density of blue starlight, which Sturl discussed, and you wind up with event rates then. In our event rates in LIGO 1, the first LIGO interferometer, is between 3 times 10 to the minus 4 per year and 1 every 3 years. LIGO 1 is going to operate and collect data for about 3 years. So if it's at the upper end, then we might be lucky and see something. Of course, even this span of numbers should be taken with some grain of salt.
What is a factor of, say, 2 in sensitivity? Do you do that?
So these sources are all now out at distances like 20 megaparsecs and far. The 20 megaparsecs is just beyond the Virgo cluster. You're out at the region where you're getting into the realm where things just increase at the rate of the cube of the distance. Okay. And so a factor of 2 in sensitivity will drive this up by a factor of 8.
Okay, so the factor of less than, so if my sensitivity isn't as good by a factor,
can you lose?
As much, or is it just a spot where there aren't as many sources?
Well, if it's a factor 2, since you're at the outer edge of the Virgo cluster, things are more complicated than that. Factor 2, I'm not sure what it would do. It may be just a factor 2 or so, or 3 in event rate rather than a factor 8.
So maybe if I the last factor 2 noise isn't necessarily as important.
Well, the important source is black hole binaries, probably. There, you're looking out to 100 megaparsecs, where it truly is a distance cubed or sensitivity cubed law. For this advanced interferometers, the distance to which you can see is 300 megaparsecs. You computed that number as well and got, what did you get in the end by? Okay, anyway, that was part of your homework. And that corresponds to an event rate between 1 and 800 per year. So you turn on in LIGO at the level where if you're lucky you see something, and after the first upgrade you should see a lot, or at least you are really quite confident of seeing something. Neutron star black hole and black hole binaries, we cannot rely on observed systems in our galaxy to get the event rate, because we've never seen any neutron star black hole or black hole binaries in our galaxy. We've seen supermassive black hole binaries that will radiate in the LISA band in distant galaxies, but that doesn't help in the LIGO band. So in the LIGO band, one has to rely on the techniques that Sturl was discussing in his lectures, but I don't know whether he used the name population synthesis or not. Did he ever use that phrase? So this is a phrase that corresponds to the following exercise. You look out through our galaxy and you study the statistics of main sequence binary star systems. Now the phrase main sequence, which Sturl used many times, but some of you may not be familiar with, just means young systems that are burning their nuclear fuel in their first phase, where they're burning hydrogen in the core. For the stars are burning hydrogen in the core. They have not yet exhausted the hydrogen in the core. This corresponds to the bulk of the lifetime of these objects. They spend much smaller amount of time burning helium in the core, or burning hydrogen or helium in shells and so forth, because they're by the time they're doing that, they burn a lot faster, and there's also a lot less energy release for each nuclear reaction. And so you look at these main sequence binaries, things that are young enough they're still burning hydrogen in their core. You look at the statistics of them. And some of these are progenitors that ultimately, when they die, they'll make neutron star black hole binaries or black hole binaries. And so you then build yourself a huge Monte Carlo simulation where you say, this is my best understanding of the distributions of the masses, M1 and M2, the separations, the eccentricities of these main sequence binaries. And you then go into that distribution, which you base on observation to the best that your observations can tell you what it is. You go into that distribution and you randomly pull out typically 1 million systems from that distribution. And then you evolve each of those 1 million binary star systems. And each one, depending on the values of these parameters that you've chosen, each one will go through a variety of complicated contortions of just the sort that Stirl talked about. Various phases of mass transfer from one to another, a star expanding into a giant phase when it converts over from burning hydrogen to helium and swallowing its companion then spiraling in and throwing off the mass in the envelope in the manner that you analyzed in a problem for today. And you wind up with the core of this star, and the smaller star that was spiraling in is a more compact binary. So there's a whole series of contortions of things that can happen. One of the things Stirl didn't really discuss much is the fact that you go through a phase in order to form a neutron star or a black hole where the core of a normal star has to collapse. It collapses because it's exhausted all the nuclear fuel that can hold it up. It collapses, there's a supernova outburst, at least in many cases, a supernova outburst. In that supernova outburst, it's generally not terribly spherically symmetric. And so the newborn neutron star or black hole may be given a kick due to asymmetry in the outburst, mass being blown off one side, you get a kick of propulsion in the other direction. Those kicks will typically, in fact usually, at least in the case when you're forming neutron star binaries, they will usually disrupt the binary. And so you're finished. And so in these population synthesis calculations, you have to put in numbers for the distribution of kick velocities. And then for what is the probability, depending on the direction in which the kick velocity is given, of the binary disrupting when the kick occurs. And if the binary disrupts, as far as we're concerned, you just throw it away. Other people may be interested in the result, but for gravity waves, we're not interested if the binary disrupts. So we want to wind up with a compact binary that will emit gravitational waves. These kick velocities and their impact on disrupting binaries are perhaps the most serious uncertainty in arriving at numbers for the neutron star black hole binaries, population synthesis numbers for these or for those. And so there are huge numbers of uncertainties, but nevertheless, this is the best we can do, is to go through this process with, say, 1 million binaries drawn from this sample. Lots of complicated physics has to be put into those evolutionary scenarios. That complicated physics is things like the kick velocity distribution, things like just how far you have to spiral in order to eject the envelope off a star. The calculation you did where you made some very crude assumptions which are not necessarily correct. And so, but along the way in the evolution of this 1 million binary star systems, you make a lot of other kinds of systems besides the ones that you and I are interested in. A lot of other kinds of systems that are actually seen on the sky, such as the AM Canvan systems, which Stirl talked about, a white dwarf star and a very low mass subdwarf or brown dwarf star. You make AM Canvan systems, you make low mass X-ray binaries, you make systems like Cygnus X1, which is a approximately 15 solar mass black hole with about a 30 solar mass blue giant companion. And so you look out through the universe and you see just how, out through our galaxy, and you see how many of those there are. And when your population synthesis calculation doesn't give the right answer, you start tweaking the input physics for things like kicks. And that's in fact how you determine a lot of the input physics, is by calibrating on the observed systems, which are not the ones that you and I are interested in, but that can be used as calibrations on the population synthesis process. When you go through all that, then you wind up with these numbers for the neutron star, and black hole binaries, which correspond then, if we look at the important things, the rate is seen by LIGO 1 and LIGO 2 interferometers, to event rates 4 10 to the minus 4 to 0.6 per year, or 1 to 1500 per year. Now you notice there's a less than or of order. That's because we've never ever seen any of these systems and so we're not absolutely sure that the population synthesis calculations are giving the right answers. There's so many uncertainties. The lower number is Vicky Calagara's estimate from studying all the literature and from her own population synthesis calculations, her own personal lower limit on the uncertainties. But this indicates that we haven't seen any yet, and you really should be pretty cautious. And then for black hole binaries, I've just assumed 10 solar mass black holes here. Stirl tends to choose 7 solar mass black holes, which would give numbers a little bit smaller. The first interferometers, again, it's 1 every 25 years to 1 every 2 years. Advanced interferometers, 30 to 4,000 per year. Now, there is yet another way in which we can make black hole binaries, and I'm going to give you a paper that I suggest you read on this. That is in globular clusters, where you had to do, again, population synthesis to analyze things, but the evolutionary scenarios are very different. In a globular cluster, what happens is the more massive, let me remind you, a globular cluster will typically have a size that may be something like 10 parsecs, 30 light years in diameter. It will contain something like 10 to the 6 or 10 to the 7 stars, something like 10 to the 6 solar masses. So the star density is very high. The star density is 100 to 10,000 or even 100,000 times higher than the star density in the sun's neighborhood. So stars interact quite easily. They have near encounters and change their orbits through interactions. If you form a bunch of black holes in here through the evolution and death of massive stars, and let's ignore whether they happen to be in binaries when they form or not, because they're heavy, turns out they will sink toward the center as a result of interactions. They find each other and make binaries, just by finding each other through sinking to each other's vicinity. Then they go through complicated 3-body interactions, which will eject one and make a binary of the other 2 that grows tighter and tighter and tighter, which ultimately spirals together and merges. And so the whole story of how the black holes or the neutron stars that are made by sinking to the center, binaries that are made by these objects sinking to the center and finding each other and capturing each other, how that population evolves is a completely different kind of exercise in population synthesis. The people who have really attempted to do this are Macmillan and Portuguese-Zwart. In the paper that I will give you, they wind up with numbers that boil down to roughly the same range. This number must be wrong, less than order 0.004. They're in the range about 0.04 to 0.6 per year, but they get a number that they claim is very definitely not 0. But the external community is not convinced it's definitely not 0. These are their numbers. For LIGO 1 and for LIGO 2, 300 to 4,000 per year. The uncertainties are surely bigger than what they quote, but these are their numbers.
So the numbers are the same from clusters?
So this is 30 to 4,000, less than or of order 30 to 4,000. This is of order 300 to 4,000.
I was looking at LIGO 1.
LIGO 1, that's where I said this should be 0.004, I think. Let me just...
Okay.
That's right. I missed a 0 here, and I missed a less than sign. So there are 2 zeros on here. Yes?
Is this assuming the same initial mass function as the field, or?
You mean in the case of clusters? I'm not sure what they assume, but I presume they assume the same initial mass function, or they may assume the old. Globular clusters are old systems, and the initial stars are more metal poor than in the field today. They may use a different mass function because of that, but I don't know. Stirl is on top of these issues, and I'm not. But they will say in the paper that I'll assign to you to read. Other questions? Okay, so that's the current wisdom. that it's really going to be up to the gravitational wave detection to reveal what the real truth is. I would not be surprised if these numbers were significantly off if it was outside these ranges. Now, I'd like to spend the next 10 minutes as an introduction to what Alessandro Buonanno will do, by talking now about the problem of computing the gravitational waves from these systems for the use of LIGO in data analysis. And we'll see how the waveforms that are computed are used in the data analysis next term. But let me remind you that the basic idea of the data analysis is that you have an incoming signal that is badly contaminated by noise. It's a sinusoidal signal that goes to larger and larger amplitude and shorter and shorter period. And you don't know what that signal is because you don't know whether there's any system there at all in a given stretch of data, or whether there's a neutron star binary there, or a neutron star black hole binary. You don't know whether it's a 1 solar mass and 10 solar mass for this system, or whether it is 1.4 solar masses and 20 solar masses, or what the masses are. So you have a huge family of templates, as we will see, typically something like 10,000 or more templates for theoretical waveforms that you cross-correlate with the observational data. And so if your theoretical waveform gets out of phase with the actual waveform by more than, say, about a radian over the entire stretch of data that you're analyzing, then you know it in the cross-correlation. If you've got the waveforms agreeing to within about 1 radian, you get a large cross-correlation which will stick up above the noise if the source is really there and close enough. If you have the waveform wrong by as much as about 1 radian out of the entire wave train, then you may miss it, or at least you certainly know it that the cross-correlation has gone down significantly. Now, how long is the wave train? Well, depending on the systems we're talking about, here in advanced LIGO interferometers, LIGO 2, it's about 10,000 cycles. Here it's more like about 1,000 cycles, maybe 600 cycles. So let's say in the worst case it's 10 to the 4 cycles, which is about 10 to the 5 radians. So you need waveforms that are highly accurate to something like a part in 10 to the 5 in the phase evolution, in the worst case. In typical cases, not quite that bad, maybe a part in 10 to the 4 in phase evolution.
Okay.
Yeah.
When you do the cross correlation, do you weight it by amplitude?
You weight it by amplitude and inversely by detector noise, and we'll discuss that when we talk about data analysis next term. And so that motivates the need to compute these waveforms, at least the phase evolution, to very high accuracy. And for the reason that you mentioned, you also need the amplitude evolution to a moderate accuracy. Now, the challenge of doing this, you see when you look at the velocities of these systems in their orbit. The orbital velocity looks something like the angular velocity times the separation of the two stars. If it's an extreme mass ratio, then it really is true. The small object goes around the big object with that velocity. If they're equal mass objects, then their relative velocity is this number. Now, the angular velocity is the square root of m over a cubed, where a is the separation, m is the total mass. And so this is the square root of m over a, is the orbital velocity. We know that the gravitational wave frequency is the angular velocity times 2 divided by 2 pi to convert from an angular frequency to a actual frequency. So that means, in fact, if you just combine these formulas, that the orbital velocity is pi mf to the 1/3, where f is the observed frequency, m is the total mass of the star. Now, if you put in numbers, total mass of the star, say between, if it's 2 neutron stars, it may be about 3 solar masses, 2 black holes, it may be as large as, say, 40 solar masses. You put in a frequency, say the frequency at which the waves first enter the LIGO band. In the advanced interferometers, that may be 10 hertz. Just no lower. LIGO can't see any lower than that. And you just put those numbers in, and you wind up with a velocity that is between 0.05 and 0.1 times the speed of light. When the waves enter the band, and these velocities just go up, beginning at a 10th or a 20th the speed of light. At the end, the relative speeds are close to the speed of light. They're above half the speed of light at the end. Now, you remember that Newtonian theory of gravity is the leading order in an expansion of general relativity equations, where you're expanding in the speed of light squared, which is of the same magnitude as m over a, just by this relationship, v over c, is the same magnitude as m over a, and the same magnitude as pressures divided by energy densities if you're not working with a vacuum. Now, when we do binary evolution, we typically ignore the internal structures of the stars, though there are some circumstances where you can't, and so we don't worry about this. But Newtonian theory is an approximation to general relativity then, let me ignore the p over rho, where you work at leading order in a power series expansion in v over c squared, or m over a. Now, v over c squared is about 10 to the minus 2 when you enter the LIGO band, but we need waveforms accurate to a part in 10 to the 5. So when you just enter the LIGO band, you've got to go beyond Newton by a couple of more orders in v over c. And by the time you get close to the end of this in spiral, the v over c expansion fails. You don't believe it at all. You can't even begin to do what you need to do, even in the lowest, at the very beginning of the waveform when the speeds are low, if you don't go up by 2 more orders, say, beyond this. So when you take Einstein's general theory of relativity and you do expansions then in powers of v over c, you go through just the kind of a process that I led you through initially to get Newtonian theory and to get linearized theory as well when we were expanding in m over r. But at each successive order, the mathematics gets more complicated, the delicacies get worse. So you do Newtonian order, we know that the key effect that appears is Kepler's laws, and the waves that are generated are mass quadrupolar. You then go on and do post-Newtonian, which was something that Einstein and Infeld and others pioneered in the 1930s. You go to order v over c squared beyond Newton, which is this also of order m over a, and you see the perihelion shift of Mercury. There's an example of an effect that you get out, the famous perihelion shift by which general relativity was tested. And the gravitational waves come from mass quadrupole, but also mass octupole and current quadrupole. You go to the next order, post 1.5 Newton. It turns out there's nothing of interest at v over c to the first power. So you go to v over c squared, then v over c cubed, and you go up by 1 order in v over c. That's called post 1.5 because the orders here are in m over a, which is the square root of v over c. Then you quote the post-Newtonian order. Here you see spin-orbit coupling, which means, for example, if you have a black hole that's spinning about this axis, you have a neutron star orbiting. The spin of the black hole drags inertial frames and causes the orbit to precess like that. Now you've worked out the gravitational waves from a binary, and you've seen that the waves depend on the inclination angle of the orbit. If you see the orbit face on, the waves are stronger than if you see it edge on. So for this precessing binary, the amplitude and also the phase of the waves gets modulated by the precession. And so you have equations for the precession that say the time derivative of the orbital angular momentum is something like 2 times the spin of the central black hole divided by the separation cubed crossed in the orbital angular momentum. The standard equation for precession, and you read this off as the angular velocity of the dragging of inertial frames, or the angular velocity of precession of the orbit. However, if both objects have spins, it becomes more complicated than this, because you have both spins are dragging the orbital angular momentum, and the orbital angular momentum is dragging both spins. And when you go up to post-2 Newtonian, you get spin-spin coupling. So you have three angular momenta by now. You have, let's put them one object here and the other object there. You have 2 spins, S1, S2, and you have an orbital angular momentum, L, and they're all dragging each other into precessional motion. You have a very complicated precessional motion coming at this order. That modulates the waveforms in a manner that Alessandro will describe. In addition, at post 1.5 Newtonian order, you have a wave tail that shows up in the outgoing waves that is this in a space-time diagram is the binary orbits in a space-time diagram. It emits outgoing waves, and some of those waves get scattered off the space-time curvature of the binary itself. They go back into the center and through and come out. And that delays the arrival of the waves. And so you see this showing up at this order. You have to go to post 2.5 Newtonian order before you see radiation reaction. And the radiation reaction that you then see is due to the Newton motion, that is the mass quadrupole radiation. We've computed radiation reaction by looking at energy conservation, but in a post-Newtonian expansion, it's way down at post 2.5 Newtonian order. The post 3.5 Newtonian order, you get the radiation reaction due to post-Newtonian waves. Post 4.5 Newtonian order, you get the radiation reaction due to this guy, and so forth. And a huge number of other effects along the way. So as you may imagine, the computations of these waveforms is a tremendous challenge, and I would guess that there have been a total of order 75 person years by now put into computing these waveforms. So I'll let Alessandra tell you about them and tell you that they are not satisfactory and that we're not finished. Okay. So
No, I don't need.
You don't need the projector yet? Okay. Yeah.
Yes. So I will cover the following 4 points very shortly. So I will explain how people in doing data analysis get the gravitational waveforms. So the theoretical templates from post-Newtonian calculations. Then I'll discuss some features of these waveforms, including the spin effects. And for this, I will show you some plots with Mathematica. And then I'll describe what is called the intermediate binary black hole problem that also Kip mentioned before. And what is the main issue here? The fact that the post-Newtonian expansion at some point fails. And as the last point, I will discuss some analytical methods that try to resum the post-Newtonian expansion and try to deal with this intermediate region. Okay, so let's start with the gravitational waveforms. So here I will refer to waveforms that are emitted when the two bodies are quite far from each other and the two bodies are orbiting along a circular orbit. And so I assume that the two bodies are just moving from following an adiabatic sequence of circular orbits. And in doing this, with this assumption, one can, and for the moment let us disregard the spin effects. So the two binary have no spin. And generally people, to get the waveform, start from the so-called energy balance equation. That is this equation here, so it's called the energy balance equation. And in this equation, E is the so-called mechanical orbital energy of the system. So it's the energy in the center of mass of the binary when we disregard radiation reaction effects. And F is the flux of gravitational waves at infinity, or the so-called luminosity function. You heard about it some weeks ago in this course by Kip. At the lowest order, this F is just given by G over, is just proportional to the product of the third derivative of the quadruple formula at Newtonian level. Then you will have corrections to it. Okay, so if you restrict to circular orbits, these two functions that are the crucial ingredients to build then the waveforms depends only on, because you are on a circular orbit, they depend only on the orbital frequency, or better, on the function on the quantity v that Kip introduced just a few minutes ago, that is the Newtonian velocity, pi mf, where f is the gravitational wave frequency. So, for convenience, I actually introduce another function that is just the non-relativistic energy. So I subtract mc squared and I divide by mc squared. It's not so important, but so if you do this, and you will have so that E. So E, as I was saying, is just a function of v, and then also the f is just a function of v. And then you can rewrite this equation using the fact that v is related to f, and f, pi f is the derivative of phi with respect to t. This is phi gravitational wave, so this object is 2 times the orbital phi. Okay, so you use the relation between v and phi, and at the end you rewrite the equation like d over dv. I'm not going to give you all the details of the, but I want just to. So you rewrite this system of equation, this equation like two equations like this, and then you can solve them. And at the end, what you get is just that, for example, t will be t at a certain reference point. these are just, this and these are just integration constants. And with this prime, I mean the derivative of the energy with respect to V.
So you didn't say explicitly that phi is the gravitational wave phase.
Yeah, so phi, oh, sorry. Yeah, because I'm calling phi the orbital phase.
The orbital phase.
Yes. Okay, so from this relation, you see that if you know E and F, you can, and you know them as an expansion in V, as post-Newtonian expansion in V, then you can expand all this and get the expression of T and phi. Okay. Now I want just to give you the expression of, just to get an idea. So E of V is I will give you just the first terms of this series.
Can I ask you one question?
Yes.
Over there, these formulas, how do they depend on V?
Well, I'm doing some abuse of notations. This is, okay?
What's the subscript on V?
On V is V ref, can be the time at coalescence or the last stable orbit or something like that. Okay, and so this is the Newtonian term. Let me introduce nu, that is just m1, m2 divided by m squared, and nu ranges between 0, the test mass limit, and 1/4 when the two masses are equal. You plug it m1 equal m2, and you get 1/4. M is the total mass of the binary. Okay, so here I wanted, so this is just the energy of the conservative part of the dynamic, so it depends only on even powers of V, as you can see. And this is the 1pn terms, the 2pn terms, and then this is known, also the 3pn terms is known, and then it would be, we'll have higher orders. Okay, so this is a typical expansion that you can have.
So the first term is just the Newtonian kinetic energy.
Yes.
Plus potential energy.
Yes.
Minus sign.
Yeah, here, because I'm using E, I'm dealing with a non-relativistic energy. So this is why I don't have the mass resistance. And for the flux, the first term, the one that comes from the Newtonian part is just, the one that I wrote right there is just nu square V to the 10th. And then also it has an expansion V squared plus V cube plus V to the 4th, etc. This comes from the
Just
quadruple
historically,
Thorne.
so the first post-Newtonian term, your 3 plus, is it nu over 12, or what, I can't quite see it.
Here?
Or 9 plus nu over 12 up above. So that's what was computed in the 1930s by people like Einstein, Infeld, and Hoffman.
I think so, because this is the 1pn.
And so if you go read long papers in literature in the 1930s, and one of these papers says the calculations are so complicated I'm depositing them in an archive. I won't bother to publish the details. And that was the first correction.
Yeah. But then people evaluated this second correction. Actually, two groups of people, Damour and Blanchet and Ayer in France, Ayer actually in India, and Will and Wiseman in the States. And so it was also a long calculation. And now we know also the 3pn, at least one of the two groups has evaluated the 3pn also contribution. And
I don't believe it. Confirms it.
So you
okay.
use 6 there instead of,
Sorry?
I mean, there's no, is the coefficient really 1 or is it?
Oh, no, I didn't write it because it's very long.
Right.
I didn't write it. No, it's very complicated.
Right, so it's
And on the contrary, for the flux, we know, okay, so this is the 1pn contribution. I'm not putting the coefficients here, it's just,
Kid uses the ampersand for that, is that right?
Yeah.
sorry?
Kip uses an ampersand, just the and sign.
Okay,
In order
anyway.
to indicate the term's life, because I mean, to me, I was shocked that the coefficient was actually 1.
You thought it was. Okay. Okay, now it's clear the notation. Okay, so this is this term here is the 1.5 Pn that contains the tail effect that Kip was talking before. This is the 2 Pn, and then you have higher order corrections. Okay, but let's go a moment to the waveform. So.
And this is all without spin.
Yeah, this is all without spins. With the spin, I give you only the final result for the phasage. Okay, so let us consider still just the quadruple. So we use just the gravitational waveform obtained with the quadruple. The quadruple formula, so just the leading term, and in that case, so the gravitational waveform will have a certain amplitude, and then there will be the cosine of phi of t. So this phi again is 2 times the orbital phase phi. Now you can rewrite this. Well, this is just a cosine, so you can write it like and then you want to take when people build templates, they generally work in the Fourier domain. So you take the Fourier transform of this H. From this moment on, I will forget about this gravitational wave written there. And this is defined like df minus infinity plus infinity, and then you have H t. Well, actually, let me write directly the expression, otherwise it will take time. And also it's generally assumed that d phi.
Integrate over t, not m. Alessandra?
Yes?
Your integrals over t.
Oh yeah, sorry. Yeah, generally one assumes that this d phi over dt is always an increasing function of time, so the frequency is increasing while the two bodies spiraling. And now, for also what Kip was saying, the phase as a function of time oscillates a lot of times, and so this phase oscillates quite violently. And so, in order to so when in general the integrand has this property, then one does the integration using the so-called stationary phase approximation. So the integral is evaluated, evaluating the zeros of the phase, and because of this assumption, this term here you can is not important. So you have to evaluate. So you can introduce a psi f that is 2 pi f plus minus phi t. Sorry, this is a psi of t that depends on f. And then you look at the zeros of this, and then you expand out these zeros, you get a Gaussian integral, you do the integration in the complex plane, and the result, I give only the result, So this h in the stationary phase approximation has an amplitude, well, yeah, there is an amplitude in front that if you evaluate at the first order in post-Newtonian series is just f to the minus 7/6.